We're going twice. One more time until it's late, unless you are absent for like a ginormous period of time next week. Alright. Are you ready? Today we're going to be talking about basically adding in the imaginary pieces to this, so our procedure really doesn't change. And then for our last problem, they're going to take the problems backwards. In other words, you get the answers and then you go up into the actual equation. So we don't have a lot to cover on here, so we can try to do this as fast as possible and then get you into your homework. The fundamental theorem of algebra, all that states is if f of x is a polynomial of degree n. In other words, they just gave me a generic degree. Where n is going to be greater than 0, meaning it has to have a degree. Then the equation f of x equals 0 has at least one root. Remember, root is the same thing as saying a solution that is complex. Most of this is very mathy language, so we're going to put in other words down. Because this theorem really is not saying anything extraordinary. All of this theorem is stating is that if we solve polynomials, we'll get answers that are either real or imaginary. You'll get one of those two answers, if not a combination of. That's all it's saying. You're guaranteed to get an answer that's either real or imaginary. What that means for us is that now we're looking at the imaginaries. So if we do our example, where we have x cubed plus 3x squared plus 16x plus 48, these will ask you to find all zeros. And remember, yesterday we talked about this idea. If they want all real zeros, you don't have the imaginaries listed. If they want all zeros, you do have to list the imaginaries with them. So for tonight, they will want the imaginaries also. Okay? But my process is still the same. I'm still going to be solving just like I was before. And what should I check to solve this equation first? Yeah, see if I can factor by grouping. First two, last two, let's GC up the first two. Last two, higher. Pull out the x squared, and what do I get? X plus 3, good. Pull out the positive 16, and what do I get? X plus 3. Do they match? Yes, they do. Which means I get to write it in the front, and then what goes behind that?
X squared plus 16.
As far as the factoring is concerned, am I done factoring?
Yes.
Why can I not factor x squared plus 16 again? Kevin?
Because it's different squares.
Yeah, because it's not a difference. There's no minus here. Now, here's sort of a nice hint for you. If you have a quote-unquote difference of squares that has the plus there, that's always imaginary. You will always get imaginary off of that type of setup when you come through. So if I want to find the zeros, just like always, we set each parenthesis equal to 0. Subtract 3 and I get negative 3. Subtract 16, I get negative 16, and then what do I do to get rid of the square?
Square root it.
Square root it. What is the square root of negative 16? Plus or minus 4i. Don't forget the plus or minus sign. Which means that your zeros are going to be negative 3, 4i, and negative 4i. Now, if you did plus or minus 4i, that's fine. Realize on any of your testing, they're going to split them. Okay? But I also want you to recognize when you do plus or minus that you have 3 answers here. Now, from this sort of section, so I'm not going to erase the bottom, just so that we can look at it while we do some properties here. So in my next section, we're going to call these properties / definitions, because we'll have a definition inside of it. The first property that they start to address once we start talking about this fundamental theorem of algebra is that if your degree is n. So again, the degree here would be 3, because that's the highest exponent. So if your degree is n, then you will get a total of n solutions, as long as you're talking about real and imaginary. That's directly related to your fundamental theorem of algebra. That leads us into this statement, which says if your degree is n, then you have that many solutions, as long as you're talking about real and imaginary. And we're also talking about if you repeat. You count how many times you repeat also. So if I look on the problem that I have down here, my degree was 3, because that's the highest exponent. And notice how many zeros I got. I got 3, as long as you're counting the imaginaries also. Okay? Does that make sense? All right, so then we have another property that sort of heads into our next definition. And that is that when we are solving and we get answers like the following, where we have something like x plus 4 times x plus 5 squared. So a lot of your homework that we just turned in, you had a lot of squares there. When those parentheses duplicate, we call this a quote-unquote multiplicity. Of the 0. In other words, if I look at the example that they just gave me, what are the 2 zeros here?
-4 and -5.
Yeah, I'm going to stack them. So I got a -4 as a 0, and I have a -5 as a 0. My marker kind of skipped there. So if we're looking at the -4, I only have one parenthesis with -4. So we state that that multiplicity, in other words, the amount of times I got that is a multiplicity of 1, because you only have that -4 once. There's only one parenthesis with it. But the -5, I have 2 parentheses with it, which means if I were to spread it out, you would duplicate that result. So this has a multiplicity of 2. This means nothing to me when I'm solving and finding zeros, because like we said before, -5 is just one spot on the number line when I plot that number. So as far as solving is concerned, I don't really care about the multiplicity. However, we're going to make kind of a little start, because this heads us into Thursday, which is that while the multiplicity doesn't tell me anything about my zeros, the multiplicity tells me a lot, and we're going to underline that. It tells me a lot about the graph. And I don't want to get into that today because we'll be doing that when we graph on Thursday. Okay? But it's good to start looking at it, start noticing multiplicities, start identifying them now. Because when I do that for graphing, then we're going to analyze what does that mean to us as far as the graph is concerned. Okay? Does that make sense there? All right, so we have one more topic to kind of close out our discussion on these zeros. And that is, what if I take this backwards? In other words, instead of giving you a problem to factor and find zeros for, what if I give you zeros and then we just kind of work back to the problem? So that'll be our last example here. You do not have one of these on your quiz, however, I think you'll either have it on the benchmark or you'll have it on the next quiz we take next week.
Ms.Kurtz,
Uh-huh.
is that a multiplicity of 1 and 2?
Multiplicity of 1 for the -4, and then multiplicity of 2 for the -5. All right, our example is to write the equation for a polynomial
Is there going to be like questions like this on our homework tonight?
yes, with leading coefficient of 1 and the zeros 2 and 1 plus I. And then you have one where there's no imaginaries and you have one where there is an imaginary with what I gave you. Which if you copy down what I gave you yesterday, I changed it a little. Not a lot, but a little. These are a little bit shady type of problems because they don't give you all the information that you need to know. So let's sort of backtrack because they gave me one of my zeros, which is an imaginary number, right? So let me go back. When I got an imaginary number, how did I get imaginary numbers? I square root a negative, right? When I square root a negative, how many answers did I get?
2.
I got 2. I got a positive one and a negative one. If you get a square root out of quadratic formula, you still have 2 imaginaries. You have one with the plus square root, one with the minus square root. So we have a property. If we come back here, we have a property that states that if you have an imaginary they come in pairs. You have to have 2 of them. You have to have one where you have plus the imaginary, and you have to have one where you have minus the imaginary. Which means for this particular problem, I have 3 zeros here. I have a 2, I have 1 plus I, and then what else do I have? If I have 1 plus I.
1 minus I.
I have 1 minus I also. You have to have both the positive and the negative. Notice the 4i works the same way, it's just a little bit easier because you don't have the a value in front. But if I have 4i, then I have negative 4i. Okay? All right. Now we have our factor theorem that states if 2 is a 0, then the factor is x minus 2. I can apply that to these imaginaries also. So x minus in parentheses 1 plus I. And then I have x minus in parentheses 1 minus I. The first thing that you need to do is distribute your negative on both of the I parentheses here. So you end up with x minus 1 minus I, x minus 1 plus I. And I'm not going to lie, distributing that out is going to be a pain. But you have a trick here. You have to distribute the i's together first. So always distribute the i's first. And you do that for 2 reasons. The first reason is every time you get an I squared, remember that gets replaced with a negative 1.
I have no idea what's going
And every time that you do this, you're going to lose all of the i's. So if I have to multiply this out, you have a 3 on 3, which means you would have to take the x and multiply it by all 3 on the inside. So you'd have x times x times negative 1, x times I. If you multiply the negative 1, I'd have negative 1 times x, negative 1 times negative 1, negative 1 times I. Then I move on to the negative I times x, negative I times negative 1, negative I times I. For the sake of time, we do not have time to do that. So I will take you down to the answer if you multiply that out and combine your like terms. But you have to remember when I combine the like terms, everywhere you see an I is going to cancel out. And everywhere you see an I squared, it would become a negative 1. If you do that correctly, you should get x squared minus 2x plus 2. If you're not sure how that happens, unfortunately, it's one of those things you'd have to come see me at a different point or ask me Thursday or something like that to kind of help you out with that because of the time constriction here. Your second task then is to go ahead and distribute once again the x minus 2 into this parenthesis. So again, I'm going to take the x times all 3, negative 2 times all 3. If you combine like terms, you would end up with x to the third minus 4x squared plus 6x minus 4. Now this idea of having a leading coefficient of 1 comes down in this step. Is my leading coefficient of 1 here? Yes, I got a 1 in the front, so I'm good. If they told me they wanted a leading coefficient of 2, I would multiply everybody by 2. That's the only change that happens. But this would be the answer to that question. And I do apologize that we don't have time to do the distribution. But the one on your homework's not as crazy of a distribution as this one. So you should be able to go through it tonight.
And this homework is due Thursday?
More than likely, you'll be taking your quiz all Wednesday, so probably Thursday.
Yeah, I know.
I think we should.
I don't know.
So did you understand?
Oh, totally.
You should take that back because I don't want it.
Yeah.
Okay, good.
I can do it.
Forward to it.
Okay.